So what's the main block diagram for most power supplies? We start off with what? Yeah, start off with a power source, right? Then what do we usually do? Then we usually run it through a transformer. So the transformer, you have to size that depending on what load you're trying to run, right? And we'll look at that. Then we come through next. We come through what? What's next? Good, rectifier. Then we hadn't got here. This is what we'll look at now. What comes next? Filter. And then what comes last on the power supply? Yeah, the actual regulator. And then this would be where our loads are attached. So of course this changes the AC voltage for us, right? And current. Most people say, what does the transformer do? And they say, well, it steps the voltage up and down. But they don't understand, if it steps the voltage up, then the current goes down, right? If it steps the voltage down, current goes up. Then the rectifier, this is converting AC into pulsating DC. And then the filter converts pulsating DC into unregulated DC. And then, of course, the regulator converts unregulated DC into regulated DC. And what do we mean by regulated DC? Nobody knows? So what do we mean by unregulated DC? That means the DC stays fairly constant, even with varying loads, right? So you've got, most people got a regulator on your car. We call them speed regulators. We call it speed control, right? You engage that sucker. What does it do? Around, not exactly, but it stays around that, right? You understand? It all depends on what terrain you're going over. So there's no such thing as perfect regulation, but it's real good. Some of our regulate, and that's one of the things when you buy a power supply. That's one of the specifications on it. It's the percent regulation, which would tell you how much the output voltage would actually vary from minimum load to maximum load. So every power supply is going to be rated at a current that it guarantees that it can maintain a fair regulation. So if you got a power supply on your little cubes, you got to look real close. It's written on the sides under some way. It says it's going to give you so many amps out, plus or minus a certain. Most of them don't give you the percentage. Okay, so this is where we're at right here. What we're going to look at now is we're going to look a little bit at filters. I think in the old book it's in chapter 3, in the new book it's in chapter 6, after you get through with all your rectifiers. But first, where you're going, there's different types of, we got two devices that we can use for filters. We have devices called capacitors, and then we have devices called inductors. The linear power supplies, which we're spending most of our time, and why we use linear power supplies, is these are the easiest to design and they're easiest to fix. And these guys handle the power. So if you've got anything that's needs a lot of power, it's going to be a linear power supply. Small power demands is usually going to be what we call a switch mode power supply. So what we're going to do is we're going to spend a little time on this device. It's called capacitors, because these are the filters that we're going to use in this class. Capacitors basically in an AC circuit, capacitors vary their opposition with frequency. They do no work, which is so weird. So current flows in and out of them, but it don't flow through them. So they actually do no work. But when you measure the current and you measure the voltage drop across it and you use V times I, you come up with a power, but we call it an apparent power. It's not real power, it's apparent power. So the only opposition that does real work is R, resistance, some type of resistance. So everything has that. These bulbs have some type of resistance in them, or they wouldn't do any work, right? You understand? But also they operate off of AC. The opposition of a circuit is called capacitive reactance. It's rated in ohms. It does no work. So in an AC circuit, we have two types of power. We have what we call apparent power. This is how much power it looks like you're getting. And then we have true power or real power, which is the amount of work you're actually getting. Unfortunately, your transformers have, and apparent power, by the way, is rated in units called volt amperes. Most people say volt amps. And then, of course, R is rated in watts. Real power. So this is apparent power. And this would be real power. And we have something called a power factor that's very important in AC. And this is real power over apparent power. And this you don't have to know for this class. And our ultimate goal is to get a power factor of 1. That means you're getting the work that you're paying for. So an engineer would use that power factor, and they would compensate for this. So what's unique is that inductors cancel capacitors out, and capacitors cancel inductors out. So an inductor is nothing but a coil of wire. So all your transformers, all your motors are inductors. And they create apparent power. What the power company does, it adds capacitance to the line to try to get the power factor back close to 1, which is pretty neat. So you're not concerned with power factor at your house because the power company takes care of it for you. But big industries, they have to take care of the power factor themselves. And they're trying to get a power factor of what? 1. That means 100%. So that means in DC, we use capacitors like little small batteries that we charge up and then we discharge them, just like a small rechargeable battery. And it's just like batteries. A battery will discharge itself, right? You know, batteries over time will do what? They'll go dead. So a capacitor is a device that has the ability to store a charge for a short period of time, and this is what we're using them for here. The ability to store a charge is given in a unit called farads. So since capacitors vary their opposition, so resistors, we can rate those in ohms. Capacitors are rated in farads because their opposition changes with AC, so there's no such thing as a 100 ohm capacitor. So what we have to do in an AC circuit, they call it sub C, and it's in ohms. We have to use this formula right here. So it's 1 over 2 pi times the frequency it's operated in times the capacitor in farads. That would be the formula we use in AC. In DC, the farad gives us the ability of the capacitor to actually store a charge. So the more farads it has, the more coulombs it can hold. Now, what's a coulomb, by the way? Anybody know what a coulomb is? It's a measurement, but it's a storage. So 1 coulomb is equal to 1 amp, but it's stored. So a coulomb would equal to 6.25 times 10 to the 18th electrons stored. An amp would be when a coulomb is what? is in motion, right? You understand? So coulombs is storing electrons. So that's what you do. These capacitors have the ability to store electrons. So they start off acting like an empty bucket. And then when we put a potential across it, all these electrons flow in here, and what do? They charge up. And eventually what happens, you hit the top, and then they stop charging. It's just like a chargeable battery. Once you charge it up to the rated voltage, it stops charging, right? You understand that? So that's what it is. If you understand a water bucket and you understand what this thing does. So in a water bucket, we store gallons, and a capacitor store coulombs. And farads gives you an indicate. So the more farads they have, the more coulombs we can put in there, which means the more amps we can get out of the capacitor. So we get some pretty good sized capacitors. And then, of course, then we can use it. Once we got a capacitor charged, then we can discharge it, right? And we use these all the time. So like a lot of times when a device goes off and you turn it back on, you don't lose anything because it's got a capacitor charge in there that holds that voltage for a small amount of time, and it keeps you from losing stuff. Then some stuff don't use that. So a lot of times when your TV blinks, you come back and your volume and everything is still okay because it's got a capacitor in there holding that charge up for a little while, right? And that's what I said. So one farad could hold 1 coulomb of electrons with 1 volt applied. So it would charge up to 1 volt. And we don't see I've never seen a 1 coulomb capacitor or 1 farad capacitor. So capacitors are usually rated in microfarads or picofarads. Now, of course, in a power supply, when we use these as a farad, we're going to use microfarads. And that's what it says. You can think of a capacitor as a bucket. The larger the farads, the more coulombs it'll hold, right? Does that make sense? Everybody okay? So this is basically a capacitor. A capacitor has 2 plates, and then it's got an insulator in the middle that we call a dielectric. And this is the symbol of a capacitor. Then we have a polarized capacitor. We don't like to use this symbol because in motor controls, we use this symbol for a normally open contact. In fact, I think I lost a job. I was in electronics, and I dealt with capacitors. And I went for a interview at Motorola up in Huntsville, and the guy showed me me and my buddy showed us a PLC print, and he said, "What's this a symbol for?" And we said, "A capacitor." And guess what? I don't live in Huntsville, so that means I didn't get the job. So Rich has done that too. That's me and the guy both, we didn't get a job. So so you live and learn, right? So we can make capacitors. I can make capacitors with nothing but 2 pieces of wire and bringing them in close contact together. I can make a capacitor. So it's really cool. So sometimes we have what we call stray capacitance. The storage size of a capacitor is determined by the size of the plates. So the bigger we make the plates, so we call these guys plates. So these are called plates. This is the dielectric. So what determines the amount is how big those plates are, right? You understand? And how close we can get them together. No, the bigger the, so if I use the same dielectric, so if the dielectric is the same material and has the same width, if I come up here and start making the plates bigger, of course I'm going to have to make the dielectric bigger. Then they have more. They can store more of a charge. Another thing we can do is if we leave the plates alone, if we bring the plates closer together, they interact with each other more, and it will hold. The capacitance would go up with that too. But we got to be careful. We don't want the plates real big, right? You understand? So a 1 farad capacitor, using air as a dielectric. Air is a pretty good insulator. Dry is a pretty good insulator. Using air as a dielectric, A 1 farad capacitor, the plates would be 1 square mile with an inch separation. I forgot that. So separating the plates by an inch. But if I could drop it down, if I could half the distance, then what would happen is my capacitance would go up by 2. But the problem is the closer we get them together, then we got charged up on each side, and your voltage is trying to push, right? Y'all understand that? Eventually, it's going to arc across, and then we got a problem. If it arcs through the dielectric, we got a problem. So it's a happy medium that we're looking for, trying to get the plates far enough to charge it up to a certain voltage, and then trying to get the plates big enough to hold the coulombs that I need to hold, right? You understand that? So what we do is we play around with dielectric, different types of dielectric to get the plates closer. But if you ever arc through the insulator, it's just like on a regular wire. So your conductors, the actual wire itself, it's rated in amps. It's rated in amps and ohms. That's all it's rated in. Your insulator, what's your insulator rated in? It's rated in how much volts it can keep in. Because that voltage is looking for ground, right? You understand? And we got commons all over the place. So this floor has a different potential than this table. And we have static electricity all the time, right? Where we get 2 devices that build up charges, and then we arc. Well, if it arcs through that insulator, we got big problems, right? You understand that? So what we're trying to do is that dielectric is going to be rated in how much volts it can keep without pushing current through the dielectric, because there's no such thing as a perfect insulator. So eventually on a wire, if you arc through that thing, then and that's what causes most spark plug wires to go bad, is they start getting goop on the outside, right? You understand it changed the opposition of the spark plug wire. It arcs through the insulator. Now you got a carbon path through there, and now you're arcing all over the place. So if you got a car that's missing, that's actually misfiring, we're not meaning your car is missing, we mean it's misfiring. And odds are it's one of your spark plugs arcing where it's what? Where it's not supposed to. You can go out there at night usually and open up your hood and look around and see which ones are. But it's always a good idea to replace all of them. The dielectric constant of the insulating periods and the distance between the plates. So we can have variable capacitors. I can change the what? Size of the plates, or I can change the distance. I can show you all these. They vary. We got some where they cross. So we have a plate out here. I'm going to draw it square, and then we'll have a plate down here. And what we do is the capacitor only exists where the plates overlap. So if I was to turn this and go in there, then I'm changing the size of the plates. So of course, to indicate a variable capacitor, we would draw the symbol and we'd put an arrow through it, right? So anytime you see an arrow, it means that the device is what? Variable. So this is the way we store a charge. So we can put it across the thing. We usually don't do it. What we're going to do is we're going to charge this thing through a resistor, because we start off with an empty bucket. And so basically a capacitor, when it's discharged, it has almost no opposition at all. So what happens is originally when you put power across the thing, then the only thing that's limiting the current flow is the resistance of your wire and the resistance of your power source. So normally if we're going to charge a capacitor, we're going to try to put a resistor in series with it. Okay, everybody okay? Yes or no? So we start off, if I was to start this off, are you okay so far? Yes. Are you asking me a question, Brian, or are you making a comment? Okay. These down here? Yeah, they're blurry to me. So we'll expect these are, so the slide itself, these are blurry? Yeah. Yeah, so this is what I'm trying to tell you, basically what it's showing you. So, And what I'm going to do is I'm going to put a switch right here. So to start off, this guy has a 0 charge. And let's say we have an R over here. Okay. So we start off, we close the switch. The capacitor starts charging. So if this was 12 volts, then we start off with the resistor dropping 12 volts at the instant we close the switch. As soon as the capacitor starts charging, it's going to charge up the voltage, right? You understand? So when it goes to 1 volt, then now my resistor is dropping what? 11 volts. So the capacitor charges slower, because this guy right here is controlling how fast the coulombs move in, right? When this goes up to 2 volts, then now this resistor is dropping what? 10 volts. The capacitor charges slower, because I is equal to what? V over R, right? You understand that? Then we come up here, when this charges up to 5 volts, we're jumping up, then this guy right here would have 7 volts across it. The charge rate slows down. Why? Because the current flow is smaller. When this charges up to 11 volts, this guy right here is charging up to what? 1 volt. Now it's charging really slow. Now eventually this guy's going to charge up to 12 volts, and when it charges up to 12 volts, the current flow in the circuit stops. So the capacitor is fully charged. So when a capacitor is fully charged, it acts like an open circuit. But it's sitting there holding these coulombs, which means what I can do now? I can discharge it into something, right? You understand that? We got 2 people that's not here. So we got it. It's still discharging. So I've got a real small resistor. I'm going to put it around it. This makes it discharge, right? So that's only a 47 ohm. And then when we press it, it does what? Starts charging what? Real fast. And you see as it gets up to the top, it starts doing what? Slower, right? Y'all understand why, right? Because it's dropping more voltage, the resistor's dropping less, so the resistor's controlling how fast the current flows in. So I is equal to V over R, right? You understand? So the lower the voltage that the resistor's dropping, the less current flow we have into the actual thing. And guys, it would take a long time for this thing. Mathematically, it never charges up to full voltage because of the resistor. There's always a little leakage through the dielectric, right? But we can get it up to around 99%. Now the math formula is pretty complicated. That actually charges it because it uses common logs. So the one we'll use is the time it takes to charge it would be equal to R times C, but unfortunately this is only 63%. So the time it takes for full charge is R times C times 5. So it takes 5 times. This is called a time constant, by the way. So that means to fully charge this thing I got over here is 100 microfarads. So time would be equal to full charge would be equal to R, which is 100K, right? Times C. What did I say it was? 100 microfarad times 5. So how long would it take to fully charge this thing? K times 100 microfarad. No, it's not 100 microfarad. I'm sorry. Hold on. It's 47 microfarad. I needed to look at my capacitor. 100K times 47 micro times 5. So how long would it take, guys? I picked up 100 microfarad a while ago. We got 1,000 microfarad down there. So this is 1,000 microfarad right here. 235 seconds. Time So your time's in minutes or seconds, right? Where your time's actually in minutes. So if it comes up to be a fraction, it's going to be seconds, right? So how long would it take to charge this? So 10K by 47 micros, so 10K, 100K times 0.0000047 and times 5. So the time is in seconds, I'm sorry. So it'd be 240 something seconds, which would be how many minutes? 23.5 minutes? Oh, 23.5 seconds. Thank you. Yeah, 4 zeros, right? Micro, 1, 2, 3, 4, 5, 6. And that's why it's nice to use that EXE key on your calculator, or it might be the E key, EXE, because that stands for, this stands for this. So you can just enter 47 and then hit that EXE key and then say minus, right, 6, and then you don't have to worry about the number of zeros they have. You know what I'm talking about? And don't everybody have an EXE key on there? Yeah. That's why it's nice to use those, so you don't have to remember those seconds. You just know that it's micro. Now, what they do to increase the size, by the way, is they make one plate that wants to accept electrons, store electrons, and then they make the other one that wants to store holes. And this allows us to reduce the size of the plates. Now, what does that mean? Well, what that means is these capacitors are polarized, which means in a DC circuit, you have to put these capacitors in the right direction. If you put them in backwards, then they're going to have tons of leakage current and they're going to blow up on you. So when I look at these capacitors, so what did I do? I dropped it. They're going to be what they call radial leads. So radial lead capacitors, these are capacitors where the leads come out the end. Those are going to have a plus sign on them or a minus sign. Most of the time I've seen them, they have a plus sign on them. This is this one. So this is called a radial lead. This is called a radial lead because it comes out the side. And what you're going to see when you roll it around. Oh, wrong camera. Oh, then I'll use this camera. So when we roll it around, it'll focus in. Let's try the other one. Because I think it focuses in better. So first of all, the two things the capacitors are going to be rated in is they're going to be rated in microfarads. So this right here is 1,000 microfarads, and then they're rated at a voltage that the dielectric can handle. So this would be 1,000 microfarad at 50 volts. So we wouldn't operate this in a circuit that had over 50 volts. And another thing, when I roll it around, you get this big old minus sign right here pointing that lead right there. That means I need to point this toward the negative, and this needs to point toward the positive. If you put it in there backwards, power supply, we have no R in it, almost no R, and we'll show you why. And, that means these guys will blow up. I'll show you a video. Can you see the little dash? It's big with the circle around it. There's a big white dash in the center. That's the minus. See that big white dash in the center of the black circle? No. This right here is the negative sign right there. Now I don't have an actual lead. An actual lead, usually they put a plus sign on the plus. The other way that they do the minus, the other way they do the minus is they make the minus lead shorter than the plus lead. See that? The problem is that when you pull it out of a circuit or when you get regular the solder, you cut those leads off, and then you lose the short lead. So that's why they do it two ways. They not only show you using the short lead at the minus side, they also put the minus symbol. There it is, right there inside that. I need to find an actual lead too, so y'all can show you that because you'll run into both of them. Oh no, this has the minus sign on it too. So this is called an actual lead right here. Actual lead, because the leads come out the what? The ends, and it's kind of like a card. This is 47 microfarad. It's only rated at 25 volts. And they're using the same feature here too. I'll find one that's got the plus sign on it. So on these and the power supplies, your capacitors are going to be polarized because what they're trying to do is they're trying to get the most farads out of a smaller size. In AC circuits, we use what we call non-polarized capacitors. To increase the capacity using smaller plates, the plates or sometimes of a capacitor are designed to accept electrons or holes. This feature requires the capacitor to be oriented toward a certain DC polarity. If you put these guys in there backwards and you have a really good power supply, they're going to blow up on you because they're sealed. And the dielectric in there has got a liquid in there. And what happens is anytime you heat something up, they expand, right? These guys are sealed up. They got nowhere to go, so they'll pop on you. So you got two ways you can pop these things. You can put too much voltage across them. You can try to charge them up to too much voltage, or you can put them in backwards. We had a guy over in the motor coach lab. We got 208 volts over there on the motor coach labs, and that's before we had lockouts on them. So now the only way you can put the 208 out is if the instructor comes over and turns it on. We had a circuit breaker over there when the last teacher before me took that. We had a guy that was putting 208 volts across capacitors and blowing them up. And the problem is that you had to lean across them to turn the breaker on. And last time I saw him, what was his name? He had a glass eye because he had lost one of his eyes. I didn't ask him how he done it. Well, because he was doing weird stuff. But that ain't all the story. This is the whole story, guys. So when he was a kid, he had his sister close his finger in his door, and he lost his finger. So we started calling him Nubby. Nubby, yeah. And he was so funny because he was one of these that put his fingers in his ear. His ear, yeah. So I'll show y'all. Installing a capacitor backwards will conduct to and get hot, and it may do explode. So that's one of the reasons we make sure we wear safety glasses in this class, because these parts can pop on you. And when you pop a capacitor, it shoots that rubber seal out on you. So a capacitor, guys, shouldn't get hot. Number one, a capacitor shouldn't get hot because there's no current flow through them. So technically, capacitors don't do any electrical work. They store it and they get rid of it, right? You understand? So this is basically a makeup of capacitors. So notice the bigger they are, one of the things, the bigger they are, it means either this is going to go up, right, you understand, or the capacitance is going up. So this is a 45,000 microfarad capacitor, and it's rated at 20 volts. And we can't see the plus lead. Mostly the plus lead will actually be measured on the screws. And they keep going down this side. This is rated at 220 microfarads. With that guy, we can store up to 200 volts in that. This is 160 volts. This will be 10 volts. This one I can't read. I can read the microfarads. I can't read the voltages because this projector gets out of focus. So we've already looked at this. So with resistor placed in series, this is going to charge that. We call it an RC time constant. So at 63%. The formula is actually it charges in toward a common log. I mean a natural log. It's E to the minus RC. So but we don't need to know that because what we're doing is we just say, okay, this is the one we're going to be familiar with. 5 times R times C. This is fully charged, right? And it would discharge in 5 time constants too. So it actually, when it charges, it actually creates a slope like this. Starts off real fast and then levels off, and eventually it would charge up to your source voltage. And these are called exponential curves. So they don't charge in a straight line. So the higher they charge, the more they charge, the slower they charge. Right? Does that make sense? And we actually saw that really good on the oscilloscope. So how long would it take to fully charge this guy? So we'd use what? Time fully charged would be equal to 8.2 K times 0.01 microfarad times 5. By the way, capacitors do not use legal engineer notation. Mainly they're rated in microfarads or picofarads. Every once in a while you'll run into a nanofarad. So 8.2 K times 0.01 microfarad times 5. Not 410 seconds because this is micro. And the answer is in seconds. What? So what'd you get? 410 microseconds. So this is a really small capacitor. It fills up real fast, right? You understand? It's just like a bucket. And that's what you need to look at. The smaller the farad. So a while ago we were using 47 microfarads. So that bucket was pretty big, right? You understand? This is only 0.01 microfarad, and this is controlling the flow into that. So this guy's going to charge real fast. In fact, this guy, you can use an ohm meter to look at these things. This guy, as soon as you hit it, it would go to infinity. It would charge to infinity. But you could take a 100 microfarad capacitor and put an ohm meter across it, and you can literally see it charge. So how fast will this one charge? Oh, no. How fast will this discharge? Well, it's going to discharge the same amount of time, right? You understand it? Because what happens is when it discharges, right, the voltage across the capacitor is going down and the voltage across the resistor is going up, right? You understand? So it discharges the same amount of time. So we use exactly the same formula. So time to discharge would be equal to 2.2 micro times 10K. So this is the guy we're going to be interested in. So what we're going to do, guys, is we're going to charge this thing up with our DC, and then it's going to discharge through the load. So this is one of the main filters that we're going to use. Yeah, times 5. Thank you. Yeah, I was just seeing if you was paying attention. You'll hear instructors use that a lot when we make mistakes. Let's do the 100 microfarads because that way it's just okay. So what's going to happen in this circuit? So I turn on my AC source. We got it positive, right? So this positive comes over here. I've got my capacitor charged. I got the positive toward that side. Then what's going to happen is my capacitor is going to charge. The only thing that's going to limit the charge would be how much R we have in this circuit right here. And we have almost no R, right? You understand that? So this guy's going to charge almost as fast as I put AC on there. So the capacitor is going to charge. And it's going to charge up to whatever the peak voltage here. So let's say V peak is equal to 10 volts. Well, this sucker is going to charge up to 10 volts almost instantaneously because we have almost no watt. We have no almost R. Okay. So what happens is this guy starts dropping down now. So this guy drops down to 9 volts. This guy's charged up to 10 volts. This diode cuts off because now it's no longer forward biased. I have 9 volts on the anode. I have 10 volts on the cathode. Now this guy's reverse bias. It cuts off. But the capacitor's charged up to 10 volts. What's it going to do? Well, here's its path right here. So what's it going? It's going to discharge through the load. How's it going to discharge? Well, it's going to discharge what? Time is going to equal to R times C. Well, the problem is that this guy will never have to fully discharge because what's going to happen is it's going to start discharging. And then right over here, 16.7 seconds, I pick up another one of these, right? You understand? Oops, sorry. So let's put our AC up here. So our pulsating DC, let's put our pulsating DC up here. Because this is a half wave, right? So I came over here like this, and I charged it up. This dropped down. Capacitor, as soon as it drops down, the diode turns what? Off. Okay. Then this goes like this, right? You understand? Then it does what again? Does this again. Sorry. So the capacitor comes over here. It starts discharging through the load. Capacitor comes over here and discharges. Then it hits right here and then charges back up. Then as soon as it hits this peak, the diode turns off, and then this guy right here comes down again, right? So what I would end up with, if this is 0, what I would end up with is I would end up with this guy right here. Now, what determines the discharge rate? Well, R times what? C. Why not times 5? Because we're not letting it fully charge. We're only letting it discharge for what? 16.7 milliseconds. And the diode cuts off. No, it's discharging through. The discharge path is here. Well, we charge it up right here. And as soon as this drops down, now this is going to be fully charged, right? You understand? This is going to drop down to like plus 9 volts. And now I have the anode more positive than the cathode, so the diode turns off instantly. So the diode is only on for this amount of time right here. Then the diode does what? Then it turns off. So the diode's turned off, right? Then what happens? Now this guy's got a path that it can do what? It can discharge. So it's going to start discharging. Well, as soon as it starts discharging, this is going to drop down. And then all of a sudden when it hits this, it's going to do what again? It's going to go back up. Then it's going to discharge. So what we end up with on this is we end up with this thing that we refer to as a ripple voltage. So that's what it's called. And all the formulas we just learned just went out the window. Because we don't have pulsating DC anymore. We don't have pi anymore. We don't have any of that garbage because it's no longer a sine wave. Now it's this DC. This is DC. Now what determines this slope right here? Well, what determines this slope is this guy right here, R. So if R goes down, it discharges faster. If R goes up, it discharges less. So the more current demand you have, it discharges faster. The less current demand you have, the slower it discharges. Now, where's my DC voltage going to be at? Where's my average DC voltage going to be at now? My average DC voltage is going to be right down the center of this thing right here. So if this is 10 volts peak, over here we'd actually get 9.3, right? So I'd have to do this. Then my AC is going to be pretty close to 9 volts. Well, it's not going to be equal to it, but it's going to be pretty close to 9 volts. Not much, but it's going to be an average, right? You understand that? And it's going to vary, though. The problem is if I come over here and drop this down like this, because my load, then my average is going to drop down here, right? It's going to be in the center. So this is why we call it unregulated, because it varies with load. So the more current load we put on it, my output voltage would go down because my ripple voltage gets bigger. And if it goes up, if my load goes down, if my current goes down, this goes up. So the average DC would actually vary with the load. Mm-hmm. What did you say? Do we have a what? Do we have a starts with F? Do we have a formula? Sure. What do you think? What do you think the answer to that question is? Sure, yeah. We can calculate this pretty easy. Well, no, not easy. So my volts DC would be equal to V peak out minus my volt ripple peak to peak divided by 2. So it's, yeah, it's under unregulated power supplies, right? Filtered unregulated power supplies. Yeah, mine. So volts DC would be equal to V peak out minus the ripple voltage peak to peak divided by 2. So all we got to do, we know how to calculate V peak out, right? Everybody understand that? So all we got to do is figure out how to calculate what? That right there. So what does it say, the formula for calculating V ripple peak to peak? No, we're trying to figure out how to calculate this guy right here. Hmm. So it makes sense, like for a half wave, this has got to hold this for 16.7 milliseconds. So one of the things we have V ripple peak to peak would be equal to I. Yeah, but this would be, time would be up here, and then this would be over C. So that would be one formula. But the problem is we know that half wave is 60 hertz, and for full wave it's what? 120 if it's 60 cycles, right? So time and frequency are inversely proportional. The other formula, the one I like to use, is V ripple peak to peak is equal to I of the load over the size of the capacitor times the frequency. I mean, all this came from is the V is equal to I times R. And then what we did is we substituted time. So that means if I was using half wave, I would use 16 for if it's 60 hertz, then I would have to use 16.7 milliseconds. So that's more numbers you have to remember. If I was using full wave, then I would use 8.33 milliseconds. That's another number you remember. But what we need to remember is, okay, frequency and time are inversely proportional. So that means they're opposite of each other. So I know that half wave would be the same as the input frequency, and I know full wave would be double. So instead of me having to calculate time, if I know the frequency, then I can use that in the formula. So this is the formula I like to use right here. V ripple peak peak would be equal to I the load times the size of the capacitor times frequency. So for half wave, using 60 hertz, I would use 60 down there. Right? That makes sense. And then for full wave, I would use what? 120. So I wouldn't have to know 16.7. Yeah. Yeah, you just use average frequency. So now hopefully half wave is the same as the input frequency, and full wave is twice the input frequency. Right? That makes sense. So you can see this if the size of if the load current goes up, right, then ripple voltage is going to go up. If the load current goes down, then ripple voltage goes down. So this is why this is unregulated. So how many different loads have you hooked up to these power supplies in DC? So that means when you hooked up a 100 ohm resistor on the 5-volt supply, the ripple voltage went up. When you hit a 1K resistor, the ripple voltage went down. And so the unregulated varies, and then we run it to a regulator to take care of that, and we'll look at that too. So the important thing that we really need to know is that, and this is why you get into these big power supplies. You know, if you first of all you're very interested in, you need to know, and these capacitors have to handle V peak, right? You understand that? So if you put a capacitor in there and you put an over voltage, you don't get the right size. And this came into play. I was teaching. It might have been this class, and the students didn't have capacitors. Well, I went down and I grabbed a bunch of capacitors, 10 microfarad capacitors. But what didn't I look at? I didn't look at the voltage. And I gave this to my whole. I gave these things out to the class, and they hooked them up, and all of a sudden they started going, pew, pew, one after the other. And why? Because I didn't give them a high enough voltage rating capacitor, so that was my fault. So, guys, everything that you've done wrong, I probably done wrong. Yeah. So of course I'm still here. So luckily, I wear safety glasses and stuff like that. But yeah. So have I blown up capacitors? Yes, I have, and that was my fault because and that's some of the things you got to really look into. That's why I'm really make sure that y'all understand this stuff. And like I said, what time is it? Okay. So these guys are in Jamico, and they're deliberately blowing up capacitors. Let's see if I've got this videos. Yeah, here we go. So we buy a bunch of stuff from Jamico Electronics, and sometimes it's fun to be able to blow stuff up on purpose, ain't it? Oh. So one time they're going to hook them up backwards. These are polarized capacitors, and the next time they're going to. I don't know if I have this set up for, but I'll put the link up there for it if y'all want to. If this actually goes up, and then after y'all watch this video, we'll. It's still loading. I don't think I set the Screencast-O-Matic up to. And this is the first time I've used this on this computer. That's what it is. That's a this is a polarized capacitor. So this is reverse polarity.
Okay, this is an over voltage test on an axial capacitor.
So over voltage is a lot worse, right? Look at all the garbage that comes out of that thing. See it expand out. See the rubber seal expanding out. You hear beeping, right? W circuit breaker.